Today is that interaction of radiation with matter. Actually, this contains concerning about that laser spectroscopy. So that is a practical field of the optics. But anyway, then I will describe only the quantum mechanical description of the interaction with matter. And radiation means that radiation is basically electromagnetic wave. So classical electromagnetic wave, classical description of radiation. Classical radiation is the electromagnetic wave. So in this case, and from the electromagnetics, we already know that there are two potentials. One is that scalar potential. Basically, in many cases, scalar potential is a function of displacement, but in general, and it includes the time t, and also the vector potential. Also, it means that magnetic field coming from the vector potential and scalar potential can make the electric field. But here we use that transverse gauge. Transverse gauge means that there is translation symmetry in space. So, and in this case, and here, scalar potential can be set with zero, because when potential can be defined that defined arbitrarily defined. So, and let's that scalar potential is kind of static field. So it is let's set zero. But here, magnetic vector potential is that the curl A equal to magnetic field, so it is let's define that divergence A equal to zero. That is the transverse gauge we call. In this case, in this transverse gauge, the electric field and the magnetic field can be defined that electric field it is partial A, partial T. It is electric field because basically, and the magnetic field is that the curl A. So magnetic field time derivative of magnetic field, concerning to the electric field. So, and by the simple vector analysis, and we can derive that electric field is like this. Here plus scalar potential. The scalar potential is zero. So we only represents that only the time derivative vector potential, because scalar potential is zero. So in this case, the energy of radiation is that special integration 1 over 8 pi is that CGS unit, and also electric field square plus magnetic field square, that is the energy. And when we define the energy, and there is energy transfer, we define that it is Poynting vector. Poynting vector is that RT function, then it's a C over 4 pi, and the electric field cross B. Here it is definition of the Poynting vector. Poynting vector is the energy current. Energy current has a E cross B direction. So and anyway, then the classical current and the J T can be found that by solving the equation and Laplacian minus 1 over c square partial t square and A t equal to minus 4 pi of c j. Here is the perpendicular direction. Here the current direction, perpendicular current direction, the divergence is zero. That is the result from the classical electrodynamics. Here, from this, but we should think about that the electromagnetic field can be dealt with quantum mechanical problems. And quantum mechanical, because electromagnetic radiations can interact with matter as quantum mechanical particles like a photon. So this classical Hamiltonian can be transferred to the quantum mechanical Hamiltonian. So, and let's start from the classical Hamiltonian to the quantum mechanical Hamiltonian. And that is the interaction Hamiltonian. And classically, let's start from the classical electromagnetic Hamiltonian, electromagnetic interacting Hamiltonian, interaction Hamiltonian is that 1 over 2m, and the momentum basically without electromagnetic field, and it's p square over 2m, that is a kinetic energy, but here, and we should think about that momentum can be transformed like canonical momentum. Canonical momentum is that E over c a, it is the canonical momentum square, plus, and electrostatic field, electric potential, scalar potential. Scalar potential is like this, and the real interacting potential. It is the interacting potential. So in electromagnetic field, it's like this. And here it is a classical electromagnetic Hamiltonian. So, and the momentum operator and the energy operator, that is that Schrödinger equation in the interacting Hamiltonian. Schrödinger equation can be found that IH bar partial t psi, that is that the function of r and t. Then it is that the Hamiltonian can be, momentum can have the like this 1 over 2m, and the momentum operator h bar over I del minus E over c vector potential square plus E phi plus V. It is here, this potential also is not only a function of R. In general case, in most cases, potential has the function of R, but in electromagnetic wave, and the electromagnetic wave has the time variation of electromagnetic potentials, so it is that R and T functional. So here it is that psi RT, that is, it is the Schrödinger equation. Here we choose that the gauge transformation. And here in the momentum transform is like P minus E over CA, that is that it is canonical momentum. So, and under this this transformation, and the gauge invariance is that A prime vector potential has plus gradient chi. Chi is kind of because this vector potential curl of vector potential is that magnetic field. So, and the gradient of curl equal to 0. So it is invariant by adding this gradient term. And also potential case, and the phi prime at the actual potential minus 1 over c time derivative with chi, because and this time derivative of chi that is anyway, then it is under invariant on the electromagnetic transformation. And also here psi prime is that time dependent exponential I h bar c, e chi, and chi is the r and t function, and also psi r t. That is that we call it is a gauge transformation. Under this transformation, and the momentum is gauge invariant, and the canonical momentum is gauge invariant. I do not prove in more detail. And anyway, then we call that this canonical momentum, and under invariant canonical transformations, this kind of canonical transformation or the gauge transformations is invariant under this transformation. Then physically, it means that the physically observable quantities are independent of any gauge transformation. So this gauge transformation is coming from that with applying the magnetic field or the electric field, and it should be invariant, such kind of transformation. So, and the curl of gradient should be 0, and also potential should have the electric field like that here, transverse gauge. So to satisfy this relation, and also we adopted this kind of function. So anyway, then in here in this case, and when we think that this interacting Hamiltonian can have the classically non-interacting Hamiltonian plus interacting Hamiltonian can be separated. So, and let's divide that Hamiltonian can have the non-interacting Hamiltonian plus interacting Hamiltonian. So from this above Hamiltonian, and 1 over 2m, and also p square plus e square c square a square minus 2 and e of c and p dot a, and plus e phi plus v. That is that then it is the 1 over 2m p square of 2m plus v t. That is that non-interacting Hamiltonian. The other parts such like the other part is that interacting Hamiltonian. So, and so then the interacting Hamiltonian can be write down as the basically, and here classical point of view, and this can be write down as the 2 p dot a, but in quantum mechanical description, and the momentum is not a quantity but the operator, mathematical operator. So it is not the p dot a but the p dot a plus A dot P in quantum mechanical point of view. So it is that minus E over 2mc and P dot A plus A dot P and plus 2mc square E square A square RT and plus E phi RT. That is that interacting Hamiltonian. So and this interacting Hamiltonian, such kind of it is important because and in the perturbation theory, and this H0, if we already know that it is electromagnetic. For example, we already know that it is hydrogen problem, and it's solved exactly. And the interacting Hamiltonian, we should calculate this interacting Hamiltonian can be deal with perturbation theory. So then here let's think that this E phi, let's think about the E phi RT. Anyway, and in many particles, and Ri is that the subscript of each particles. So we should summation with all kinds of particles. So in this case, in the summation I and volume integration and E phi RT, and also discrete particles can think about that this Dirac delta function. It is R prime. It is a Dirac delta functional problems. Then also, here you can write down in the volume integration E rho R phi RT. That is that here it is this kind of delta function means that the particles of each charged particles, then in many cases summation with I can be dealt with that it is kind of charge distribution. So it is a charge distribution here, and this charge density is kind of and multiplication of the summation with the Dirac delta function, because many Dirac delta function means that point particles in the summation with very many particles, many particle summation can think about that it is the charge distribution. So and here in this case, and the total number of particles, it is the volume integration with rho. That is that it is a total number of particles, and here we call it is the density of particles. So in here let's define that this term, the first term has the current density, and also JR. Let's define that. It is definition 1/2m and summation with I and pi delta R minus Ri without vector potential, and plus delta function minus R minus Ri and pi. We call it as a particle current. Basically, it is a Hamiltonian operator. It is Hamiltonian operator. Then when we define that it is particle current, then this first term of interacting Hamiltonian of the first term is that minus E of C volume integration with current density dot vector potential. That is this first term. In classical field is that P over m is the velocity, because in classical mechanics momentum is the mv, so P over m is the velocity. But under electromagnetic field, because this gauge invariance or the canonical momentum with divide by the m over p and e over cm. It is not a velocity. So, and under the gauge transformation or the canonical momentum is not a velocity. Divide by m is not a velocity. So, and anyway, we should think about that. This current density is that here real current, the current velocity in real cases, and the velocity is that P over m minus E over mc vector potential is a velocity, because under the gauge transformation. So the J current density is that there are two parts. One is that coming from this P of m, it is the P of m2, so it is kind of current, is kind of velocity. In classical, the base concept is the classical velocity. So classical, it is we call is JR, is that that kind of current. But another velocity term coming from the vector potential. So vector potential term, it is the minus E over mc and vector potential RT and rho. It is a new kind of operator of particle current. And here, in the physical meaning of this current is that it is general current. We call it is a paramagnetic current. But it is minus means that it is a diamagnetic current. We already know that from the general physics, and by applying magnetic field, oscillating of the magnetic field, it induces that the Lenz law. Lenz law makes that the diamagnetic field. So that is coming from this term. This term is coming from the diamagnetic current. That is a result of the Lenz law. So by defining this concept here, real interacting Hamiltonian, the overall interacting Hamiltonian is that the volume integration and minus E over C and J dot JR dot A RT, that is coming from the interacting Hamiltonian, and plus E square over 2m from here, 2mc square rho r and a square rt plus e phi rt and rho. That is a final interaction Hamiltonian. So it is by applying magnetic field by applying the electromagnetic wave, it means that like a photon or the laser, and interacting Hamiltonian can be written like this.